Welcome everyone. We'll continue our lecture on parameter estimation, and in this lecture I'm going to start by first giving a brief introduction to a broad topic, which is system identification. Actually, in system identification we start by choosing a model to deal with, and the source of that model could be from physics. For example, first law of thermodynamics, Newton's law, Kirchhoff's laws, and so on. So if we have a physical system and we can derive the equations that describe that system from these physical laws, we can do that. Otherwise, sometimes we don't really know the exact relations that relate the different variables together. In that case, we depend only on taking measurements from certain experiments. Most of the time we can combine both methods, like we know for some components of the system the physical laws that describe the system, and some parts we need to do some experiments to decide their relations. So a combination of physics and experiments could be used in driving models. The experiment itself has to be designed. And one of the important factors in designing an experiment for system identification is to select the input signal, because if that input signal is not actually rich enough, and I mean by the word rich is that it's not capable of exciting the dynamics of the system so that they appear in the measurements, then that input signal is useless. We also have to decide the measurements, which signals we are going to measure and how often we are going to measure them, and this is related of course to the sampling interval that we have discussed in the previous piece of the lecture. Now once we decide upon that, we select a certain structure for our model, and there are different structures available in the literature. We know, for example, that we can represent the input-output relation by the transfer function, whether in the S-plane or the Z-plane in continuous or discrete time. We could also represent the relation between the input and the output using the impulse response of the system, or using state space models. Of course, we have to decide whether we are going to deal with a deterministic model or stochastic. And in stochastic models we have some signals that change randomly with respect to time. Actually, in our course here we will only consider deterministic signals. We are not going to consider the stochastic signals. The parameter estimation then follows that. We have to decide which algorithm to select to calculate the unknown parameters of a system, say. And there are two main algorithms that people usually use: the least squares algorithm and the maximum likelihood algorithm. We will talk mainly about the least squares, but we will mention briefly the maximum likelihood. The parameter estimation also needs actually initialization, and that by initialization I mean at least the initial parameters that we have to start from. We could also put some bounds on the estimates so they don't go unbounded. So there are factors related to the choice of the different parameters for parameter estimation. We have seen in the model reference adaptive control, for example, that we have to select the adaptation gain. So this is one of the parameters that is normally present in system identification, and that's what I call tuning parameters, like the adaptation gain. Once we do the experiment and we come up with some parameters to represent the unknown parameters of a given system, we have to go for a next step, which is the validation of the results. because sometimes there is an error either in designing the experiment or in choosing the measurements to be collected, or in the algorithm to the appropriate algorithm to be used. So anyway, we have after we get some answers from the experiment and the calculations, we have to validate these answers, and if they are appropriate, then we can take them. Otherwise, we have to look back again and see if we have to repeat parts of the identification process. So these are the main points that we have to consider in system identification. Actually, it is a topic which is very important, and there is a textbook. The main textbook actually in that subject is called System Identification Theory for the User, and this is by Liang. He is a Swedish author, and he is the author actually of the System Identification Toolbox in MATLAB. That's why I recommend that you go to the MATLAB channel on YouTube and search for the system identification. You'll find a series of videos on system identification by Liang that gives a good understanding of the basics of the process of system identification. However, in my lecture here, I'm going to depend on chapter 2 from the textbook Adaptive Control by Ostrom and Wittenmark, because this summarizes the basic ideas that we need for adaptive control design. Okay, we'll start now by giving a brief introduction to the least square estimation. Suppose that you have some measurements, output measurements. I call that y. So this is measurement, and that measurement is given in terms of some parameters. So the parameters here, psi, represent the system parameters, while phi 1 up to phi n, these are known functions. So I would write here, this is the measured output. Phi known functions, and psi parameters of the system, the true parameters of the system. Now let me give an example to illustrate what I mean by this model. This is a difference equation of a linear time invariant system. So the output is yk, and the parameters are a1, a2, and b1. So a1 would be psi 1, a2 psi 2, and b1 is psi 3. While the known functions here, which I refer to them by the symbol phi in the definition, this will be yk minus 1, this is phi 1, yk minus 2, this is phi 2, and uk minus 1, this is phi 3. So this way I was able to write the equation of the system in the form of a certain vector phi transpose, which is composed of the known functions, times psi, which is the parameter. You will notice in that model that we define the output as a linear relation in the parameters. So the parameters here, the parameter vector appears here as a linear component in the equation. But that does not mean that I'm only dealing with linear systems, because if you consider this difference equation, which is non-linear because of the sign term here, still I can put it in the form which is linear in the parameters. If I select the vector psi to be composed of a, b1, and b2, a, b1, and b2, and the vector phi transpose to consist of, this is phi 1, this is phi 2, and this is phi 3. So as you can see here, this is a nonlinear system. Still it is linear in the parameter vector psi, and this is again a valid form that we can use in least square estimation. So psi is unknown, unfortunately, normally in most systems. That's why we have to guess the value of psi. So I'm assuming that I have a guess theta, and I'd like to see how to select the best guess theta that would make the error in the model as small as possible. So if I calculate the output based on theta, I would call it y hat, because this is not the true output, it is a guess of the output, and that would be equal to phi transpose, which is the non-vector functions, and theta, which represents the guess of the parameters. I'm going to define an error signal epsilon, and this would be the difference between the actual output of the system. This is the actual output, and this is the calculated output. So y hat is calculated based on the guess theta. Now what the objective is to select theta such that the summation of the squares of the errors would be minimum. The error is the difference between the actual output and the calculated output based on the value of theta. I square that. It takes the sum from k equal to 1 to t. So t here actually is not the continuous time, but it is an index which take an integer value, and k is the sampling index. So I start from sample number 1 up to sample number t, and I try to find the value of theta that would minimize the sum of the squares of the errors, and this is by definition is the least squares problem. In order to do the minimization, I'm just going to introduce some mathematical background. Suppose that you have a function f which is a product of x transpose x. X is a vector that is composed of n components from x1 up to xn. So if I like to write f, it would be x1 squared plus x2 plus x2 squared, so on, up to xn squared. So if I differentiate that, I would differentiate it with respect to x1, so that give me 2x1. This is the gradient, of course. Then 2x2, and so on, up to 2xn. Eventually, I get 2 times the vector x. So the differentiation of x transpose times x would be 2 times the vector x. If I would like to differentiate the function f, which is a transpose x, or similarly x transpose a, since f is a scalar. So as we mentioned before, the transpose of a scalar is the same scalar, so these two quantities are actually the same. If I take the derivative of f with respect to x, then I would write this as a1 x1 plus a2 x2, so on, up to an xn. I differentiate with respect to x1, so that would give me a1. With respect to x2, that would give me a2, and so on, up to an. So the result would be just a. So anyway, in order to do this differentiation, it's better to put it in the form x transpose times the constant vector, and then you just ignore the x transpose, and the result of the differentiation would be just a. If I like to differentiate this quadratic function f(x), which is equal to x transpose ax with respect to x, then I will differentiate first with respect to the first vector. So that would give me a times x, plus I'll differentiate with respect to the second vector x, but then I have to take the transpose of the quantity, so that would give me x transpose a transpose x. So I moved that x here. So the result would be A transpose x, and that will lead to A plus A transpose times x. So this is the result of differentiating the quadratic term. Now we'll go back and see how to apply that to our quadratic function in the summation of the errors squares. We defined v as 1/2 the summation of epsilon squared, where I, the index of time, goes from 1 to t, and t here is an integer number. We define the error as the difference between the measurement and phi transpose times theta. So we can write a vector E, which is composed of epsilon 1, epsilon 2, and so on up to epsilon t. And the components of that vector would be y of 1, y of 2, up to y of t. And here I would have phi transpose of 1, phi transpose of 2, and so on up till y phi transpose of t, and that's multiplied by theta. I'm going to call this whole matrix capital Phi and call this vector y. So the result would be the error vector is y minus the big matrix Phi times the parameter vector theta. Now again, this is v, and here I can substitute the summation by just the inner product of the vector e. It's E transpose times E, and then I will differentiate that function with respect to theta. The differentiation, this is a quadratic term, so the differentiation with respect to E would give me E, and the differentiation of E with respect to theta, that would give me from here minus phi transpose. So that's minus phi transpose times E. I can substitute now for E. So this is minus phi transpose, the capital matrix phi, times y minus phi times theta. If I put that equal to 0, I would give the least square estimate of theta, and that will be given by phi transpose phi inverse times phi transpose times y. So this is what's called least square estimate of the parameters, and that's what we are going to use. However, you will notice that this expression requires what's called batch processing, which means that we are going to collect all measurements of y from time 1 up to time t, and we construct the corresponding information matrix phi, and then use all the information all together to calculate the estimate theta. This is not really what we need in adaptive control. In adaptive control, we need to update the value of theta at each sample, but this is a subject that we are going to talk about in a coming piece of the lecture, not in this lecture. So anyway, we have some notes here that theta, the value of theta as calculated here, is actually minimizing v, and the reason for that is that v was assumed from the beginning to be a quadratic function. So we know that when we take the derivative to 0, what we get is actually a minimum. In order to calculate the value of theta hat, we require the inverse of the matrix phi transpose phi to exist, and that actually is related to some conditions that we are going to see later on the input. The input has to be exciting to the dynamics of the system, and if that happens, this matrix will be invertible and we can calculate the least square estimate. Finally, in V, you will notice that V is equal to 1/2 the summation of epsilon 1, epsilon 2, and so on, up till, say, epsilon t, epsilon squared. That, as you can see, weighs the different errors equally. So if we like to give different weights to different measurements, we could put here some constant W1, W2, W3, and we can use these weights in order to say give more weight to measurements that we trust, or to give more weight to recent measurements as compared to old measurements. So we can use that in different ways in adjusting our estimates. However, what we did was just a method that doesn't actually give a different weight to every measurement, but similar weight to all of them. This is a numerical example just to illustrate how we can implement the least squares formulas that we derived. So we have here the measurement index. So this is the sample number 0, 1, 2 up to 9, and the corresponding value of u. So this is u of, say, k, and the corresponding measurement y of k. Now, if we assume this to be the difference equation that relates the output to the input, so we form the vector y. We start here from y2. Why I started from y2? Because I noticed that if I use here k equal to 2, I will need, say, y of 1, y of 0, and so on, which are available in the table. But if I use here, say, y of 0, then I would need y of minus 1, y of minus 2, which are not in the table. So the choice here of, or the starting index to be 2 here, that's just to make sure that I have enough data to fill the matrix phi. And if so, if you take k equal 2, then you will need y of 1, which is here, and then y of 0, which is here, u of 0, and u of 1. This is will give u of 1, and this will give you u of 0. And from the table, I can pick up the value of the required value. So, for example, I need here y of 1. This is y of 1, which is 0, and u of 1 is 1. So this would be 0, and this would be 1. I need also y of 0, which is 0, and u of 0, which is 0. So I will have here 2 zeros. If I do the second row, I'll need y of 3. This is y of 3, which is 0.77. So here I will have 0.77. By the way, y of 2 is 0.24. This is 0.24. And I need y of 2. So this is 0.24. Y of 1, which is 0. This is 0. I need u of 2, which is 1, and u of 1, which is 1. And so on. So I can fill in the vector y and the matrix phi. Once I do that, I will have the formula for calculating the least square estimate of theta, which is phi transpose phi inverse times phi transpose y. This is phi, this is y, so I just will directly substitute in the formula and calculate the estimate theta hat. So this finishes my introduction to least squares, and we'll see in the coming piece of the lecture the main theoretical properties of the least squares and how we can modify the least squares to make recursive estimation online so that we can use that in adaptive controllers. Thank you.